And up next we have Sheldon Campbell from UC Irvine, who's going to talk to us about astroparticle anomalies.
Great, thanks, James. So this is a new talk, a new topic. I think it's very exciting, a lot of fun, and I'd love to hear what you think. So I'm going to focus on astroparticle anomalies as best I can in the 15-minute version. So it's going to cover a wide variety of observations and talks. And sorry I can't explain them all, introduce them all. So apologies to the students, but feel free to come and ask me about anything you saw here afterwards or during questions. I think it died. OK, so isn't really looking for low significance anomalies just ambulance chasing? And so part of my job here today is to try to convince you that there are actual benefits here to paying attention to 2 sigma, 3 sigma anomalies. So part of the motivation of that is that when you have a signal that's out there, but it's very dim, hasn't come out yet, and then we start to see it. Where do we first see it? At the region of highest sensitivity. So that could be the direct detector that xenon maybe had just the right properties to see it first. For indirect detection, probably the brightest area is the galactic center. That's maybe where you get a first hint. But then you get initial hints. These initial hints will motivate models, make predictions. Where else do you expect to see a signal? WIMP paradigm expects to see signal in dwarf satellites, and so we look there. It's very robust. Then spurious anomalies come up all the time. They go away. So we look, we pay attention. But if it's real, it grows in significance, and we want to pay attention to that. Then correlated signals begin to emerge quite randomly in the next most sensitive regions. And that gives us a lot of information about what we might be looking at here. And so for annihilating cold dark matter, like I said, dwarf satellites. If you're looking for very cold annihilating dark matter, where you have a lot of very small concentrated substructure, then maybe you're looking for Andromeda. The inner halo is good for warm annihilating dark matter. The outer halo for decaying dark matter over a wide field of view. And so where that next signal is really depends on what we're looking at here. And where we see it can give us some very helpful hints. And this is kind of the point. So paying attention to weak emerging anomalies and seeing the correlations between them can really give us a lot of information about the underlying theory as it emerges. So direct detection. So this is really the original astroparticle. Searching for astroparticle dark matter, traveling through our lab, and we try to see it. This is a kind of a nostalgic plot of a few years ago. Some nice anomalies sitting here for us to look at, lots of experiments, ruling them out. Theorists tried really hard to make these anomalies lie on top of each other and still not be ruled out, and it was a lot of fun, and we learned a lot. What remains is a gamma modulation. That's a bit of an enigma. Luckily, we have new sodium iodide detectors coming online that will probe this in new controlled settings. Anais will be able, 112 will be able to, with 5 years of data, should be able to see the modulation to verify that it is indeed there in another detector. SABRE will come online, 2 detectors, one in the north hemisphere, one in the south hemisphere, that will really tell us if we're looking at the same phase of modulation, such as the dark matter wind, or opposite phase, such as a seasonal effect through weather, maybe. And cosinus as well is another interesting idea, using sodium iodide as a cryogenic calorimeter. This, at low temperature, is allowing them to able to do particle by particle discrimination. Very exciting. So if it's still confusing after SABRE, here they'd be able to particle by particle really try to understand where each event is coming from, which is something that discrimination is needed. So now we move on to astrophysical radiation, gamma rays, cosmic rays. And we have some things to discuss. This is a very exciting topic right now. Kev already told us very deeply about the 3.5 keV X-ray line. Very, very interesting. We're keeping an eye on it. And we had an excellent review. So I won't talk about it anymore. So with the rest of my time, I will begin starting with the GeV Galactic Center Excess. a lot of interesting developments over the past year or so. Fermilab came out with their own analysis now and verified that there is a robust unidentified emission coming from the galactic center region. It is roughly consistent with dark matter annihilation, what you would expect in the particular energy bin. And you can even, depending on the foreground model, have various high energy tails coming out as well. A lot of discussions, especially over the last year. There's been a lot of evidence suggesting a possible pulsar origin for the galactic center excess. So let me go over those very briefly. First, came out was the idea that the distribution of the pixels in the region behave more like a set of unresolved point sources, such as pulsars. Pulsars have the right spectrum to explain what we're seeing here. And so if you see something that looks more like this rather than something smoother, such as you might expect from dark matter, then that suggests that it would be pulsars. And so that seems to be what the data is saying for the existing foreground models that we have right now. Also, Fermilab did an analysis where they looked for pulsar candidates, and they found a lot of possible point sources that have the right spectrum to be pulsars. And so this is suggesting that with more data, maybe they are beginning to resolve this unresolved population. And it appears to be consistent with the pulsar hypothesis. Also, recently, there is a foreground modeling now where the excess appears to take the shape of the X-shaped bulge. I don't know if you can see, but there are some contour lines here that are in the follow the infrared observations of the bulge. And they lie right on top of the excess for this particular model. And that suggests then that the excess may be coming from stellar populations within the bulge, such as pulsars. And that really would not be consistent with dark matter. One caveat to that is this shape is produced by dynamical instability. And so if you had some dissipative dark matter that did collapse down into a disk and you had a dark disk, then it is possible that this instability would also apply to dark matter, and the dark matter may have the similar shape as well. Unfortunately, at TEFPA just recently, just a few weeks ago, Schutz gave a nice talk, very preliminary results using the Gaia data, looking for such a disk, and there is no sign of such a strong dark disk. So that seems to not support that idea. So now I'm going to talk about some of the cautions for why you might want to be careful about ruling out the dark matter interpretation completely. First off, let me start with this bottom comment here. If you're going to start talking about that this might be a dark matter interpretation, already you have to contend with the fact that it has, just by coincidence, if it is dark matter, happens to have a very similar spectrum as pulsars. And we know there are pulsars in the galactic center. We don't know how significant they are, but this is going to have to be, by design, a two-body problem. And one way you could estimate that is just by looking at the LMX speeds that have been resolved in the X-rays and count those. And you know, in populations, I have so many LMX speeds, and I also have so many pulsars that are typically around there. And that already gives you about 4 to 23% of the excess being from pulsars. And that's significant. We're already approaching order 1. And so you can't have negligible component of pulsars. That seems very unlikely, unfortunately. So it doesn't, if you're going to consider dark matter, it doesn't make sense to say, I'm going to consider Occam's razor where it's probably predominantly one or the other. Once you say dark matter, you have to contend that the pulsars will be a significant fraction of this. So what is that fraction? Well, that's going to be difficult to say, of course. So some of the arguments, looking at the distribution of pixels, the problem is with the current technology that we have and foreground modeling, the residuals that you have are not very stochastic. There is a lot of leftover structure within these residuals. And that's just the level of our foreground modeling today. And so it's very difficult to make comments based on the small-scale structure of pixels because a lot of this correlated structure is probably not real. And so that's going to weaken any kind of argument based on the structure of pixels. to develop this non-Poisson template formalism, they'd want to really try to mismodel foregrounds in such a way to reproduce these kinds of things and see if you're still picking out an underlying unresolved point source population. Similarly, in the region, this is modeling of the 3FGL catalog, point sources near the galactic center, which is right here. And given the point spread function, the number of sources, the spacing between these is about the size of another point source. And so if I mismodel my point sources, here's an example of one point source, and you fit them, modeling them with the power law and exponential cutoff typically, and it can do very well, but a lot of times the cutoff in the spectrum is faster than exponential. And so then at higher energies, I end up over subtracting. Or here's a region here where I'm going to be over subtracting what the data has here. And when I over subtract, if there's an underlying diffuse component, I remove that, and I leave the space in between, which look like more point sources. And so the point sources that are being seen as being potential new pulsars, you want to be very careful that you wait until you actually have verification that these are indeed pulsars. They could be relics of incorrect modeling. So there's a lot to be careful about here, and it's a very, very difficult problem to try to solve. Okay, so I would say the dark matter interpretation is still very much alive. So if it's there in the galactic center, could it be there in the galactic halo? And even way back in 2015, a little unsung paper came out that says, actually, yes, when we try to model the distribution in the halo, we do get an excess here that is unexplained at just the right energy that produces a signature of dark matter very similar to what we see in the galactic center excess. And there have been very few papers following up and looking at the halo. Again, it's a very hard problem, and no one wants to put themselves out there. But I've seen other analyses in other fields of view that seem to back up this up, that there is a galactic center excess type signal out in the halo. And once we have it out in the halo, and if it's dark matter, now we're suddenly interested, is it extragalactic? Is it galactic structure? Can we actually see the dark matter substructure? And so you could take a power spectrum. And just this year, there was an interpretation of the power spectrum of the gamma rays where you're just masking all the structure, and you just are interested in the high latitudes, masking all the point sources, masking the galactic plane. And at the high energies, you get a result that is very consistent with an unresolved collection of extragalactic blazars. It has a spectrum of blazars, and it's approximately Poisson distributed. So that's a good dominated structure by extragalactic sources. But then down here, just at a GeV, where our signals are, you have something new turning on. We're getting extra structure here, and that is not consistent with any known emitter. Okay, so they say this could be dark matter subhalos, but in our analysis we assumed whatever the emitter was Poisson distributed, and so we can't really, that prevents us from making a strong interpretation here. So a new analysis is going to need to be done with the hypothesis that this could be dark matter subhalos. It could also be leakage in low energies. The PSF is very large at low energies, so if you have leakage outside of the mask, you might create additional power. So that's something else they're considering. But once you have structure here, then you want to consider cross-correlating with extragalactic galaxy catalogs, cosmic shear, and all those things. And those are done. And they see positive correlations. Of course, galaxies correlate with gamma rays. Gamma rays correlate with galaxies, I should say. And so that's very exciting, but it's still hard to interpret. You can make star-forming galaxy models that describe all of these. You can make blazar models that describe what is seen. And so there's still a lot of work to be done here to make interpretations that will test our hypotheses. So let's move on to cosmic rays. There's neutrinos, but neutrinos right now is at high energies. So an ice cube is at a stage where astrophysical signal is all an anomaly and not an anomaly at the same time. It's not clear what it is, and it doesn't really have any structure yet. So we'll wait for more data. In cosmic rays, we have the positron excess, where the positron fraction wants to rise at energies above 10 GeV. And this has been considered for dark matter. where you can have, say, TeV scale dark matter annihilating and creating electrons and positrons. So that's a nice story, but then the problem is you run into problems when you look for the associated gamma rays, which we don't see. And so it's very difficult to find a dark matter interpretation of this that is not ruled out. Not impossible, but difficult. But this year, there's been a publication about observing Compton halo around Gaminga pulsar and a neighboring pulsar here, PSR B0656 + 14. And the energetics of this synchrotron is at the right magnitude to describe, to account for the excess positrons that we see here. And so it is quite plausible that these pulsars are throwing positrons at us, and that's our source. Hawk did their own analysis of this and did a preliminary presentation at ICRC. In their, if you look up their proceeding, it says they will show the result in the talk. But I talked to Steve Barwick, who was there, and he said their conclusion was that it wasn't enough to explain it. But he thought there were a lot of uncertainties. It seems like the energetics are right. And so again, Occam's razor suggests dark matter doesn't seem to fit here, and we have a very nice candidate. And so it seems that, OK, the details need to be worked out, but we can suppose that we're being dumped on with a lot of positrons, and that's going to make dark matter searching with positrons very difficult for us. OK, well, the energetics here are not enough to produce antiprotons. So what do we see there? And oh my goodness, would you believe it? So the error bars from AMS are so tiny now. So people have gone to a group here has, over the past year, done heroic work to model this and try lots of different propagation models and so on. And it just comes out, here's the residual without dark matter, here's the residual with dark matter, here's your new dark matter component. It's exactly where Galactic Center Excess would want you to be. So for lots of different productions, it looks great. So here's BB bar here. Sorry, is that right? Up here. Here's BB bar. Red. So blue, this is a sigma annihilation cross-section. This is the mass of the dark matter. So Galactic Center Excess kind of wanted you around 50 GeV. The antiprotons would pull you up a little bit to 60. But it all looks very good. And so it really appears like there can be a coherent picture emerging here with this GeV excess from the Galactic Center. It looks like dark matter annihilation. In many ways, this appears like a WIMP signal that we've been looking for. The significance of the scenario, of course, is still very weak. There are lots of uncertainties and foregrounds and propagation and all those things. There's a lot of wonderful work, a lot of mysteries for young cosmic ray physicists to work out. It is also notable where the signal is not seen. We have not observed the excess in the gamma rays in the dwarf satellites yet, which is where we've been looking for the WIMP signature. Also, you would expect to have already seen the synchrotron. Given the magnetic fields we've observed in M31 and M33, the synchrotron should already be visible, and it's not. So whatever scenario that you may be thinking about, you need to be able to take these into account as well. But if we're seeing dark matter, then we keep an eye on these signatures, and we expect the existing excesses to grow in significance, and the other excesses will continue to emerge as we continue to look. Thanks.